I think I skipped some things in between. So let me just go to that, which is section 27. Right. This is the Schwarz reflection principle. It is basically a particular example, particular case of analytic continuation, right, which is useful in fact for at least in quantum mechanics and so on. This is a bit useful. So I will just describe this bit. You remember for analytic continuation what we said was that, I mean, if you have, well, the most important point was that if there are two functions, two analytic functions which are, so there is some analytic function f1 and f2 in some region, and if they are equal in a set of points which has which has a limit point, right, some sequence of points which has a limit, okay, in that case, so if these two are equal on let's say zi, where z1 z2 is a sequence which has a limit point, and this sequence has a limit point. Limit point, or I think in the book most of the time they use the term accumulation, which is the same. Limit point or accumulation point is the same. Okay, so if these two are equal on all these points, and these points have a limit point, then we said that this f1 must be equal to f2 in the entire region where they are analytic, right? And the reason why that was simply you take the difference between these two, then the function which is the difference between these two, f1 minus f2, is 0 at all these points, but we already have seen that the zeros are isolated. You cannot have a limit point, accumulation points for the zeros. So therefore, it must be identically 0. That is the argument. Okay, so I mean the usefulness of this was that if I take two regions, let's say, here I have function f1, here I have function f2, okay, and in the overlap region, so f1 is analytic in this region, f2 is analytic in this region, and if in the overlap region f1 is equal to f2, then you say that f2 is the analytic continuation of f1 to this region, and vice versa, f1 is the analytic continuation of f2 in this region. Right? The point of this was, I mean, this would have been completely useless if without this theorem, because you see you could have some another function, let's say f3, which happens to be this equal to f1, right? And then you can also say that f3 is the analytic continuation of f1. However, this theorem tells me that f3 is equal to f2. So analytic continuation is unique in this sense. So this was the main point. Now, okay, here of course you see when we say f1 and f2 are defined here, and we are talking about some region here where they happen to be equal, right? Now there's a slight generalization of this, and the generalization is the following. Suppose I am given f1 in some region, okay, so it is analytic in this region, but not necessarily on this line, not necessarily say on the boundary. In the interior it is analytic. So f1, and similarly there is another region, let's say, so here is my region r1, this is region r2, and here is some function f2, analytic function. So f1 is analytic in region r1 inside r1, so not on this boundary, in the interior of r1, so in the interior. Okay, and f2 is analytic in r2, again in the interior, right? So we don't know whether f1 is analytic here or not. Similarly, we don't know whether f2 is analytic here or not. However, f1 and f2, we'll assume that f1 and f2 are continuous here. Okay, so f1 and f2 are continuous. Let me just call this as a C. So C is the boundary which is common to R1 and R2. Okay, so C is this boundary which is, which is the boundary of R1 as well as the boundary of R2 here. So it is continuous on C. Okay, and furthermore, F1 is equal to F2 on C. So these are the conditions. So we are saying F1 is analytic in the interior of this region, F2 is analytic in this interior of this region, F1 is equal to F2 on the common boundary, right? And F1 and F2, of course, they are equal. So f1 is continuous on the boundary. Therefore, of course, f2 is also continuous because f1 is equal to f2, right. So these are the main conditions. Then the claim is that f2 is an analytic continuation of f1 in this region and vice versa. Okay. So this is the idea, and the proof is very simple actually, because you remember we use Morera's theorem. Morera's theorem says that if some function is analytic, then its integral around any closed contour vanishes, any simply connected closed contour vanishes, right. So let's just take any contour. So take any contour is like this, okay. So let me just say the following. So what we are saying is that f1 is analytic continuation. In other words, what we are saying is that there is some analytic function here in this entire this R1 and R2, this entire region, this big region, there is some analytic function h of z in this region in the R1 union R2 union C. You take the union of all of these regions. R1, R2, and the boundary altogether, such that we are saying there is some analytic function in this, such that h of z is equal to f1 of z in R1. It's equal to f2 of z in R2, and is equal to f1 is equal to f1 or f2 because they are equal on C. So that's what we are saying. This is the meaning of the statement that f2 is analytic continuation of f1 and so on in the other region, because what we are saying is that now in this entire region I have an analytic function which becomes f1 here and becomes f2 there, right. Okay. So we first of all define this function h of z is equal to f1 in region R1, f2 in region R2, and on the boundary is either f1 or f2, which is equal. And now what we want to show is that this function h is analytic. So this is the question mark here. Is this the way I have defined this function? Is it analytic or not? Right. This is what we want to prove that it's analytic. Okay. So then all I have to do is just take any contour. Okay. Let's take a contour which is entirely inside the R1 and integrate this h on that contour. Well, it's obviously 0 because in that region h is simply equal to f1, and by assumption f1 is analytic, right. So that's trivially 0. Similarly, if you choose any contour here, that's also trivially 0 for the same reason, because there the h is equal to f2, right. So the only thing I need to prove is some contour which has part of it lying in the region R1 and another part in the region R2, right. So we want to show that here it's 0. Well, this is again, one can do it because I can consider, so here's my contour. So consider this contour like this, right. So you go like that and then again come back like this and continue. Okay. I can just add and subtract this part of the integral, right. But in this part of the integral, here h is equal to f1 and this integral vanishes. Okay. Similarly here, here the h is equal to f2, so again the integral vanishes. So therefore the integral of h around this contour vanishes. Okay. And then by Morera's theorem we conclude that this function h of z is analytic everywhere, right. So integral hz dz on any contour C, where not C, C I will use I don't know, let's call it gamma. Okay. Any contour gamma which is inside this region, inside this R1 union R2 union C, right, the integral vanishes. Therefore h is analytic. Okay. So this is a okay. This is just a slight generalization of what we already said before, because here I am just assuming that these two are equal on one line where I am not sure whether it's analytic or not. Of course, we say that it's analytic everywhere at the end. So it's a slight generalization. Okay. So now let me go on to say there is something called Schwar's reflection principle. The idea here is the following. So here is my z, the complex plane, right? Remember, this is the real axis, and that's the imaginary axis. I mean, that's the way I'm drawing always. The horizontal one I call as real axis, and that's the imaginary axis. So this is the real part, real axis. That's the imaginary. Okay. Now, suppose there is some region D, some region. Let's just call it D. There is some region D with whose boundary is some segment of the real axis. Okay. So I'm basically in that situation, except that this region is now in the upper half plane. Huh? So the above the real axis. Okay. Okay. So what I'm given here is that there is some function f of z, which is, I know that's analytic in this region. Okay. Furthermore, suppose that this f, so this is analytic, and further assumption that I'm making on this function is that this function becomes real on this line, on the real axis. So the condition is that this function on this f on the real axis is real. Okay. So this is my these are the properties that this function satisfies. It is analytic here, okay, and here it is real. Okay. I mean, a simple example, just take a function z itself. Take f is equal to z. Right? Z has a property when I mean z is equal to x plus iy. Right. So when the real axis means y equal to 0. So at y equal to 0, this function becomes real, right? So I mean, but more generally, this is just an example. So more generally, I'm given some function, analytic function, which happens to be real on the real axis. Okay. Then the statement is that you can take the mirror image of this region. Okay. Whatever that, the mirror image of that. Let's call that this region D bar. D bar region, just to, I mean, this bar is just like is a complex conjugation of that, right? Because after all, mirror just means if a point is x plus iy, when you take the mirror, the y becomes minus y, you know? So it becomes like x minus iy. You know? So it's okay. And then the statement here is that the analytic continuation of this function in this region is simply, so okay, write it. So then the statement is that analytic continuation of f to the region D bar is given by some function g of z, which is simply you take this function. So remember now z is in D bar, so z is somewhere here. Because I'm defining this g here. Okay, z is here. So if I take the image of that z bar, it will come here, right? And there, of course, the function f is defined, right? So I take f of z bar. Okay, so it's a defined. The function is defined there, right? And then take the complex conjugate of the whole thing. Okay. So this is the let's define some function like this. So this is just a definition. It is just saying that if you give me a point here, I define a function here, just which is obtained by go to the mirror image, evaluate the function f which is defined in this region, and then take the complex conjugate of that. Okay. So that's my definition of this function g. Okay. So now what we want to show. Okay. So let me write like this. It may not like this. So I just define a function g, okay, in D bar, okay, which is defined like this. That's a definition. Okay. So now what we want to show is that we want to show that this is the analytic continuation of that here. So first of all, I need to show that already within this region, this function g is analytic. Okay. So in other words, what I need to show is that already if I take any closed contour here, the integral of G around this contour should vanish, right? That's what I want to show. But then again, let me okay, this is F here. So let's take the image of that here. Okay. So now you see that when I integrate this G here, by definition, you see the value of G here is simply the value of F here, and take the complex conjugate of that, right? So perhaps maybe it's better to do it in the following way. So I'll take this. There's some complex contour here. Okay. So there's this. I have to integrate this contour. So let's define this contour by a parametric equation. So as I go around here, Z will change, right? In some particular way, and how it will change, it will depend on one parameter only, because this is a one-dimensional line, right? So I can write the Z on this contour as Z as a function of one parameter t, where t goes in some interval. I don't know, t goes from say 0 up to 1. So it's say at t equal to 0, this is this point. As I increase the t, it keeps going like that, and finally at t equal to 1, it comes back. Okay? This is the equation of this curve. I mean, a curve can be expressed by giving all its coordinates, expressing all the coordinates as a function of one parameter. This, I think you are familiar with that, right? Think of this t as a time, for example. It's just and imagine a particle is going around like that, right? So as the time changes, this particle is going like this. Okay? So you can always write it in this way. Huh? So I want to take G of Z, dz along this contour. Let's call this contour gamma. Well, that's the same as G of Z dz by dt, t going from 0 to 1, right? That's the meaning of that, right? Because Z is a function of t, and when you move around the curve, what is changing is a t. So I can write it as dz by dt. Okay. But now let's use this definition. So what this is 0 to 1 f z bar dz by dt, right? I mean, Z, now you see for every point Z here, the mirror image is Z bar here. Okay. So just as there is this I can rewrite it as the complex conjugate of the whole thing, fz bar dz bar by dt integral 0 to 1, and take the complex conjugate of the whole thing. You see, if you just start from here, take the complex conjugate of the whole thing. That means taking the complex conjugate of that and the complex conjugate of that. Okay, when you take the complex conjugate of that, you get this. You take the complex conjugate of that, just z bar simply becomes z, right? T is a real parameter, so that becomes, so this is the same as that. Okay, but this we know is 0. Okay, because I mean, z bar, this point is simply the image of this point here, and I'm just integrating f around this curve. Okay, and since I know f is analytic here, this thing inside the complex conjugate, this part is 0. Of course, the complex conjugate of 0 is again 0, right? So this is 0. Okay. Okay. So what we have shown is that if I define a function like this in this region, then that function is analytic in this region, because I'm considering such closed curves which are entirely inside this region, right? But now I can use a previous theorem. The previous theorem was what? I'm given one function here and another function here. They are analytic, and if I can only show that on the boundary this f and g are equal, then I'm done, right? So let us see what is the value of the. So let's look at the value of g in this on the real axis. So on the real axis, well, g of z is by definition f z bar complex conjugate, right? But when z is real, so when we are looking at this point, z is real, z bar is equal to z. So z is real, And one of our assumptions on the f is that f on the real axis is real. So its complex conjugate is the same, right? So we see that, I mean, so this implies, I mean, here I'm using the fact, this part is being used here. This is the only place I'm using this so far. But once you use that, then you see that this implies that G on the real axis, on G on, I mean, G is equal to F on the real axis. So, okay, so that therefore we conclude using the previous theorem that G is an analytic continuation of F around here. Okay. So it's convenient because sometimes, you know, when you come across a physics problem where a function is defined in the upper half plane, okay, and it happens in many applications that, in fact, on the real axis it turns out to be real. So then you immediately know what is its analytic continuation in the back. So you just evaluate, yeah, you go to the take a point here, go to the mirror image, evaluate the function there, and then take the complex conjugate. So this is the basic way of, I mean, in such situation you can analytically continue like that. Okay. Any question here? Okay. Is okay? Any question? I'm just trying to see what I have to say next. Yeah. Please feel free to ask questions. You have a question? Yeah, go ahead.
When we want to check if a function is another continuation of another one, those kind of analytic continuations are sometimes unique or
No, it's always unique. I mean, yeah, it's always unique. Yeah, I mean that was the original theorem where we said that if two functions are equal on a set of points, which has a limit point, then the two functions are unique. I mean, then they're equal everywhere.
My question is, if you have a function, can you find 2 or 3 functions which can be an analytic continuation?
No. They'll be always unique. I mean, you see, unless it happens. I mean, in all of these examples that, I mean, even for example, geometric series example I gave you, geometric series example, right? Okay, the question is, yeah, whether it's okay, let me just say it in a bit. I mean, so the situation is the following. So I have some region, here is some function, I have some function here, and let's suppose I consider some path, okay. And I mean, as an example, let's take this explicit example. This geometric series 1 plus z square and so on and so forth. Take this analytic function. This is the analytic function. This is defined in z less than 1, right? This is convergent series. So if I draw this curve here, so this is unit radius. This is the z equal to 1 point, okay. And this unit radius. So here I have defined one function which I call f of z. Okay. Now this I know. Here I can actually sum it up. This is convergent, and I know I can sum it up, and this is the same as 1 over 1 minus z. Okay. This function is defined only here. However, this function is defined everywhere except at z equal to 1. Right. This one. So now. So question now you can ask the following. So what I mean, okay, exclude this particular point. Here it's singular. Okay, just exclude this point, but what about this point here? So question I can ask is that I mean, if I analytically continue this function up here, when I say function I mean this one, okay, this here, what is it going to be? right? And what I tried to argue to you I think last time was that here this function will be simply 1 divided by 1 minus z. Is unique. It cannot be anything else. Okay, and the way to show this is, for example, if you draw a curve like this here, connecting these 2 points, okay, then you can start, you know, at this point, this object has the radius of convergence, which is this series has a radius of convergence like that. Okay, now I can start moving up here, okay, for example, and then I can again obtain the series, a corresponding series, because after all, I mean, this series is well defined anywhere inside the disk, right? So in particular, it's well defined here, right? So I can, you know, I can even again go ahead and compute all its Taylor expansions there, Taylor expansion coefficients, and write down a series around that point. Okay, but now that series will have a radius of convergence. Of course, it will be all the way up to that point, but more. In fact, it will have a radius of convergence like this here. I mean, no, I've not drawn it very well. You know what I mean. I mean, up to again, the radius of convergence will be this much. Right? But there is so this has gone a bit beyond the original region because it has gone beyond here, and so this analytic continuation will define the function here. All right. Again, if you sum that up, you will find that again this is equal to 1 divided by 1 minus z. And now, if you can keep going, you come here, for example, and then again find a new series. It will have such a radius of convergence, and like that you can keep going. Okay, but it will be unique. That is the point here. Because remember, I mean, what were we saying? I mean, the general theorem was this. So here is some function f. Okay, now I want to analytically continue to, okay, forget this particular example, just generally. Now I take another region, and I want to see what is, I mean, there is some analytic continuation f2. Okay, some analytic continuation from f1 to f2. So what is the property of that? First of all, f2 must be analytic here, and f1 must be equal to f2 in this overlap region. Right? Now imagine that you come up with another function. Suppose let me call it f3, okay, which is again analytic here, and again it's equal to f1 in this region, but it's not equal to f2 in this region. That's not possible from the previous theorem that the first theorem that I stated last time, right? Because then you will have a situation where f3 is equal to f2 here, both are analytic here, but f3 is not equal to f2 in this region. That's not possible, right? You remember the statement was that if two analytic functions are equal in any region or a curve or even a sequence of points which has a limit point, okay, then the two functions are identically equal. You understand? You see the point? No? I mean, so say, suppose there are two functions. So let's call this region R2, this region, and this region is R1. Suppose there exists two functions which are f2 and f3, analytic in R2, okay, and both are equal to f1, are equal to f1 in the overlap region R1 intersection R2 in this region. Okay. Then that theorem that we discussed last time, then that implies that f2 is equal to f3 in the whole of R1 R2. Right? So it's unique, you see. Is that does it answer? Yeah. Because f2 minus f3 will be identically 0 here, because f2 and f3 are equal to f1, so the difference will be 0. So any Taylor expansion here for f2 minus f3 will have all the coefficients 0, right? Because it's identically 0. So any number of derivatives will just keep giving you 0, 0. So every term in the Taylor expansion is 0. So f2 minus f3 is identically 0 in the domain of analyticity. Right? So that's why it's useful, that the fact that the analytic continuation is a unique sense. I mean, it's not, yeah. Okay. Any other question?
can we say that that function is analytic coordination model?
Yeah, sure. I mean, so let's say, for example, here there is another region here, say R3, okay, where again here I have another function. Say here I already used F3. Let me call it F4, which is analytic here, and it's equal to F1 here, right? Then F4 will be analytic continuation of that. So this is the way you construct. I mean, you keep going, right? And then you try to cover up the entire complex plane except for this few isolated points where there is singularity, or maybe branch cuts, or there could be also branch cuts. So I mean, do as much as possible, as much as you can, to cover as much of the complex plane as possible by considering such regions where you have some analytic function, there's another region, another analytic function, but they happen to be equal in this overlap. And then all of this entire set of functions that you get in different regions, that defines one unique analytic function, whose values in these different regions are F1, F2, F3, etc. Yeah. I mean, we will discuss in the last chapter a particular example of this situation which are called in the context of hypergeometry. Last chapter meaning fourth chapter, differential equations. We'll discuss hypergeometric functions. Those are a particular example. Is an example of such a situation where it will turn out that it will have singularity at several points, okay, with even branch cuts between those points, right? And you'll have some. I mean, the only way you can express the hypergeometric function is actually in terms of a series. So there will be some series which will be well defined in some region, in one region, right? But in another region, it's not well defined. So you have to, there is another function which is again another hypergeometric function which is defined there. Then you show that the two things are equal in the overlap region. So this is the way you move around. But I mean, I think it will be a very explicit example of this. Very complicated structures where we have even branch cuts. We will discuss that. Okay. Now, so finally, again, before I move to the saddle point approximation, let me also just say one thing, which is again useful. It will be useful in quantum mechanics. Sometimes it happens that say there is some function which has a branch cut. Okay. So it could happen that I mean, in many applications it happens the following, that so there is some function f, it's analytic everywhere, is analytic except I mean, so a function f which has a branch point has a branch cut, say starting from some real number, some real point to infinity, Okay, so let me draw it. It's easier to draw it rather than. So there is some point. Let's call it x naught. So right, and I have a branch point here, and then I take a cut from from x naught to infinity along the real axis. Okay, so this is the cut. So this is the branch point, and of course there is at infinity also there is a branch point, and you are connecting the two branch points by a cut like this. And this function is analytic everywhere else except apart from this cut. So this function is it's analytic everywhere else. F is analytic everywhere else. Okay. And furthermore, we are also another information which is given to us that this function f is real on the real axis. I mean, of course, in the branch cut, it's not well defined, so it's not a unique. I mean, when the very fact that it's a branch cut, it means that it's a multi-valued here, right? As you go around, you come back with some phase and so on. But suppose it is given to you that f is on the remaining part of the real axis, f is real. So f is real on the remaining part. Of the real axis. Okay. Then it turns out that actually you can construct precisely this function f, right? If you just knew, if you just have the, I mean, so many times the situation is like this happen. You know there is some function, but you don't know the explicit form of that function. Okay. From some physical reasoning, you know that there is an analytic function defined here, but it has some branch cut here. Huh? And furthermore, for some physical reasoning, you know that this function is real on the remaining part, okay? But you don't know what that function is. So, and the only thing you know is what is the discontinuity as you go along the cut, okay? Suppose this all is known to you, okay? Now, the question is, can you reconstruct the function everywhere else just from this information? You have the knowledge of how much discontinuity is there, right? And this information is known, then can you construct it? Okay, this is what is called, this goes under the name of dispersion relations. Dispersion relations. Okay. So let me try to, furthermore, you need a little bit more information. That the function f, I mean, you have to also say some behavior at the infinity. At infinity, how it behaves like. Huh? So one more information is given, that the function f of z goes to 0 faster than 1 over modulus z as z goes to infinity. Okay, it goes faster than that. Okay, I mean, what it means it goes faster than that is that if you z times fz also goes to 0 as z goes to infinity. That's what it means, right? Okay. I mean, all this in many physics problems you get already the boundary condition of physical reasonings, you know, etc. So okay, let's say these are some. I don't know whether you will see this in. I don't think in George's course you will see this. Maybe you might see it in the advanced quantum mechanics course. Some examples of dispersion relations, but I'm not sure if you'll see it. But in any case, it's good to sort of see this. I mean, to see that it can be done. And the way to do this is that, well, if you give you some point z, I mean, it doesn't have to be here, anywhere, but not on the cut, huh? Away from this cut, some z, then I can use the Cauchy integral representation for that, right? So Cauchy integral representation would be f of z is integral of f z prime over z minus z prime minus z, isn't z prime minus z? Yeah, 1 over 2 pi I around some contour integral, some closed contour, right, which surrounds z. So now what kind of a closed contour I can choose? We have a branch cut here, so of course I have to take a sheet, right? By the way, when I said f is real on this, it means that there is some sheet on which f is real here, right? Because obviously, if I had, suppose I started with with a given sheet where f is real here, right? Now, if I go to the next sheet, when I go across this and come back, so there will be some face in general, right? So then this in general it will not be real anymore, right? So all I'm saying is that there is one sheet where f is real on this, the remaining part of the real axis, and we are working in that sheet. So we'll try to compute this function f at an arbitrary point z in that sheet. But of course, if you know that, then you can extend it to any sheet. So since you know already the discontinuity, you can just go to the next sheet. It will just multiply by some faces and so on. Okay. So here is a branch cut. So a closed contour that I can draw is something like this. So I take this here above the cut, okay, then below the cut here, and then go around a large circle and come back here. Okay. So this is again a large circle of radius r, capital R. And then in the end, I will take the limit r goes to infinity. So of course, you see that immediately this part of the circle, this circle doesn't contribute anything, precisely for this reason. Right? because you see, I mean z is some finite point, So z prime we are saying is a large radius, so z prime goes like capital R times some phase, right? I mean, so what I'm saying, this contour has 3 parts. So let me, can I erase this part, because otherwise I don't have any space to write. Shall I erase this? Okay. So the contour C has 3 parts. One is the integral over the the circle of radius capital R. So this is what I call gamma R. Okay. And then this part, which is plus, let's write it like this, x naught plus I epsilon. You see, I am just above the cut. This plus I epsilon is just to indicate that above the cut. Cut is on the real axis. So just above the cut, to all the way up to infinity plus I epsilon. Again, this is just to keep remembering that it's upper part. Plus minus, because I mean here is the orientation is from the opposite direction. So this will be from again minus x naught minus I epsilon to infinity minus I epsilon. This minus I epsilon indicates that it's below the cut. So this is the full thing. I mean, I put a minus here because initially this was here and that was there, right? Because of the orientation, right? So I just put a minus here and exchange this here. Okay. Now first statement is that this part of the integral vanishes because of this condition, right? The reason is that you see on this z prime is capital R times e to the I theta. Okay. And let's say theta is going from 0 to 2 pi, for example. Then this is I mean dz prime picks up capital R. This is 1 over R, so R cancels. Okay. But fz prime is goes to 0, the integral. So this part drops out. Okay. So this goes to 0. So here we are only left with that. Okay. So let's write this a bit more. Yeah, I can erase here. So what we have here, so f of z prime is in this on this curve on this line. So that is the same as x naught plus I epsilon. X plus I epsilon. Yeah, that's what it is. Divided by z prime, which is x plus I epsilon minus z. Okay, and I'm integrating dx from x naught to infinity. Okay, because z prime here, z prime is simply on this curve. Z prime is equal to x plus I epsilon. Right, x is the real part, and I epsilon is this small imaginary part up. In the end, I will take epsilon to 0 limit. But it's this. So that's I'm just integrating x from x naught to infinity. So that's this here. Here, on the other hand, it's minus x naught to infinity f of x minus I epsilon divided by x minus I epsilon minus z dx. Okay, that's what it is. Okay. Now in the denominator I can easily put epsilon equal to 0 because there's no problem, because z is, remember, z is some other point here, not on the real, some other point here. So x minus z is never 0, right? It's always something finite, so I can, without any problem, I can just forget about I epsilon, right? So this I can get rid of. So then this difference simply becomes, so therefore the conclusion is going back, so this was f of z, right? So f of z simply becomes the integral of from x naught to infinity, limit epsilon goes to 0, of f x plus I epsilon minus f x minus I epsilon divided by x minus z. Yes. So it's a discontinuity. You see how much when you cross the branch cut. What's the difference between that f of? So it's just the value of f little bit above minus the value of f little below. Okay. So it's exactly once you know the discontinuity, you can compute this. Okay. Now, okay, so far I have not used this all the other information. I mean, this is a very general statement. If you know here I have not used anything else. For example, I said that there was a sheet where f is real, right? So if you do that in that sheet, you can see that actually the difference between these two, right? Because remember, when the function f is real here, then the analytic continuation of the function from here to there is just taking the complex conjugate, that thing before I told you, the Schwarz reflection principle, right? So that means, Schwarz reflection principle says that that f of x minus I epsilon. So now I use Schwarz reflection principle. Okay. Well, that is the same as, so here, the value here, or the value here, is the same as the value up there, and then take the complex conjugate of that, right? So this is the same as f of the complex conjugate of this, which is x plus I epsilon, and then take the complex conjugate of the whole thing. I mean, you remember the Schwarz reflection principle, right? This was okay. So I can substitute this here. So this is the same as f bar x plus I epsilon, right? So both are at the same point. Okay, same the upper part. Okay, so this is the same as 2i. Sorry, there is a 1 over 2 pi I forgot. There's a 1 over 2 pi I here. So this is a 2i times the imaginary part of the function f, right? Because f minus f bar. So 2i, well, that cancels, so you get 1 over pi integral x naught to infinity dx over x minus z times the imaginary part of f x plus I epsilon. Right? And of course, I had to take the limit epsilon goes to 0. Okay, so it's going from here to there. I use the fact that f is real on this sheet. If your function doesn't satisfy that, you just stop here. You cannot go to the next step. But already this is a very powerful formula, because all it's saying is that if you, for some physical reasoning, suppose you know that what the discontinuity is here, then that is enough to determine the function at any other point. Of course, when you have additional information that function f is real here, okay, then you can further reduce this to that formula, which means if you just know the imaginary part of the function at, say, on the upper one, okay, you can also write it in the lower one, but there will be just a minus sign there. But meaning that convert this guy into the f bar of x minus I epsilon. Okay. Either way, I mean, you can choose one of them. So if you know the imaginary part on the upper part, upper or lower one of these cuts here, then that information is enough to consider the entire analytic function anywhere. Okay. So this happens. I mean, in some physical problem, this is what you can easily find out these discontinuities, but you don't know what the function is. Okay. In that case, you can use this formula to construct that function. Okay. So hopefully you will see some examples of dispersion relation in quantum mechanics course, maybe in the next semester. Sorry? Yeah, it's well in that particular sheet. Then, of course, if you go to the next sheet, there will be the usual, I mean, multiplication by phases and so on. Yeah. Not just phases, could be also shifts. For example, if it is a logarithmic singularity, then you know that as you go around, there will be additive shifts. So then it depends on the nature of the, yeah. But I mean, this formula, if you stop here, this formula will give you the information on any sheet, right? Because what will happen in the next sheet, it may not be real here, right? But this formula was general. I have not used anything else. No. So all you need to do is just take whatever sheet is on that sheet. You should know the value of the function. I mean, the difference of the values of the function up and down. If that information is given, then you can construct the function f in that sheet. Okay, any question on this? Okay, now again the next topic is a saddle point. Yeah, this is again something which is very useful for quantum mechanics. Not just quantum mechanics, I mean actually for many problems. So the problem is the following. I have to integrate something. Suppose it turns out that you have some problem where I need to integrate this quantity e to the power of w times f of z times g of z dz on some contour, not a closed contour. I mean some open contour, and this is a parameter w. So obviously the result will depend on the w, and of course also on the contour c, right? The result of the integral. And we'll so in general, of course, it's very difficult to integrate. I mean, some complicated function f and complicated function g, it will be almost impossible to integrate this explicitly. Okay. Of course, if f was a Gaussian, f was a quadratic polynomial in z, you can do that integral. And for some particular choices of paths, you can do it. Gaussian integrals you can do. But in general, the function f may not be Gaussian. Okay. I mean, you can have, for example, if this function is some polynomial in z, you cannot do, I mean, not quadratic, higher. Okay. You cannot do this exactly. You cannot do this integral. Right? So I mean, you need, what you want to do is you want to kind of estimate this. Try to find a good approximation to this, but approximation in some limit, obviously. The limit that often in physics, which is very useful, is the limit where absolute value of w goes to is very large. It's almost going to infinity. So very, very large. So in that limit, can I find a good approximation for this? Okay, this is a question. Actually, I mean, in the physics application, at least in quantum mechanics applications, what happens is that this w is related to the inverse power inverse of the coupling constant. I mean, the coupling constant is something, the interaction strength, no? Coupling constant. So this goes inverse to coupling constant. Actually, it's a square of the inverse. Okay, but so and the w goes to, is very large, is basically the same statement as that the coupling constant is small. Okay, so this is a good approximation for small coupling constant. Okay, that's what happens. And I mean, often, I mean, this kind of thing. Let me just say one word before doing this. You know, you have done already harmonic oscillator problem, right? In quantum mechanics, you can exactly solve it. I mean, it's quite amazing that you can really get the entire spectrum. You can solve energy levels and so on, right? Not just in 1 dimension, also in 3 dimension. You know, you can get all that. But what if the potential was slightly different? I mean, so for harmonic oscillator, the potential energy was proportional to x square, right? That was the potential energy. And that is the reason why we can exactly solve from this point of view, is that this f is just Gaussian, x square or z square, no? So you can exactly solve it, because Gaussian integrals you can exactly perform. That's the reason for this. Now, suppose that it was not this thing, but you also put some x to the 4 term. Okay, and in fact, let me do the following. After all, if you try to draw the potential energy for x square, it's like this here, right? The potential energy x and p. Okay, but what if you slightly change it to deform it like this? Suppose I have potential energy like that. Okay, this you can always do it by, for example, adding a quartic term. Okay. Yeah, I mean, for example, write the potential energy as x square minus something x naught square whole square. Okay. So then you see at x naught and minus x naught the potential energy vanishes, right? At a large x, of course, it will go like cortic, so it will go much more faster than that, right? And somewhere in between, it goes up to the maximum. I mean, at x equal to 0, v is just x naught to the 4, right? So this is some relative maximum. This is x naught to the 4 relative maximum, and then so this is the shape. This is called double well potential. Now this is a very, I mean, if you want to do exact calculation, you cannot do it. It's already, I mean, although I just slightly just added a quartic term here, but already it becomes impossible to solve it exactly. But what you can do, so what you can do is that suppose x naught is first of all far away from each other. So these potential wells these are called wells. These are far away. So you might imagine if a particle is sitting here, it wouldn't know too much about that, right? So it will just care about the potential in the vicinity, in the neighborhood, right? So there it looks like a harmonic oscillator. So you would imagine there will be levels like this. If you draw the energy levels, first one is half h bar, then 3/2 h bar, and so on and so forth. So there will be levels like this. Similarly, here there will be levels. If the particle is sitting here, so it doesn't know too much about that, it will be like this. However, and you might imagine that, I mean, after all, I mean, classically, suppose some particle has so much energy, there's no way it can cross this barrier, right? If total energy is this, it cannot cross the barrier, right? Because kinetic energy, I mean, this is the potential energy. Total energy is conserved. So, I mean, the only way it can happen is if kinetic energy becomes negative, right? But that's not possible. It's always positive, right? So there's no way classically it can go, right? But quantum mechanically, you find that there is some small probability that a state here can go over to there. Okay, this is what is called the tunneling probability, right? And in fact, it turns out that the real ground state is a superposition of these two ground states. Okay, the true ground state, it will have a smaller, slightly less energy. Okay, and of course, the tunneling probability will depend on how far this is and how high this is, and so on. No? It will depend on all that. If the barrier is, of course, infinity, then there will be no, right? But if the barrier is finite, then there will be still some tiny probability. But in order to discuss these things, it's now this is what I'm not going to explain to you how this works out. There's some WKB approximation to do this, and you can rewrite the transition probability in terms of such an integral. Okay, where this f is basically the potential energy. Okay, but in those cases you cannot do exact integrations. But maybe you can ask the question: what happens if, say, I want to just estimate, try to find a good approximation for that? So this is the kind of problem. So we are looking for an approximate answer, but we want to be pretty good, approximation. And that approximation becomes better and better. What I'm going to describe to you is going to become better and better the larger the W is. Okay, that's so. Okay. So what is, I mean, so for going back to this integral, f and g are analytic. I will assume f and g are analytic. Okay, in some region where c is included. C is, of course, in that region. In some region which includes C. And what else I have to say? This, although W is complex, but it really doesn't matter, because I mean, I can take W to be real, because after all, W is always W times e to some phase. Let's say, now that phase I can just, it's a constant phase. I can just absorb it in the definition of f. Right? So without losing generality, I can take W to be positive real, because the argument, I mean, the phase I can always absorb in the definition of f. So I will just take W to be real and positive, and very large, what else I have to say? Right. So what we will do is, I mean, it's clear that, I mean, if you think about this function, this part, forget this. This is not so important. The important point is W is large. So we are looking at that to get large contribution. You want this to be large. So, I mean, this is e to the power. I mean, if I write it explicitly, e to the power of W times the real part of f plus I W imaginary part of f, right? That is exponential e to the WF. To make it large, say magnitude large, you want the real f to be large, right? Largest possible that you can imagine. The larger it is, the larger the contribution that will be, right? Okay. And in fact, you can see if W becomes very, very large, then the dominant contribution will come from precisely the place where real f is a maximum along the path. You remember, we already saw that for an analytic function there is no maximum of real part has no maximum or minimum, right? Anywhere, right? It's no maximum. We saw that. But what we are saying is that not the maximum when you go in all possible directions, but along the path, along the C. Okay. There, of course, you can have a relative maximum because that's a moving in one-dimensional line, not in all possible directions. Okay. So this will be, of course, the contribution will be maximum when the real f has a relative maximum in that contour. So let's say I have some contour. I look at that point where real f is maximum, which means you go this way or that way, real f becomes less. Okay, then that will be the maximum contribution, right? Because it will be large. But also another thing is that, I mean, imaginary f, if it starts changing as you go around, that is not very good because this is oscillatory, right? So it will start cancelling the contributions, right? So you want also the imaginary f doesn't change, imaginary f stays constant, at least in some small neighborhood of that point, so that there will be no cancellation. You see, if imaginary f even changes a little bit as you go around, then since W is large, W times imaginary f will become very large. So there will be large changes. So large fluctuations on the faces, and there will be cancellations. Okay? Because after all, I mean, this e to the power of that object, this is the same as e to the W real f times cosine of W times emf plus I sine of W times imaginary part of f, right? I just wrote this, the face e to the I times W imaginary f is that. And cosine and sine, you know, are oscillatory functions. So if this varies as you, so let's say this point is x naught, I mean some z naught, and you move around, if as you go this way or that way, if imaginary f starts changing, okay, then this will start oscillating rapidly, and there will be mutual cancellations when you integrate. So since we are interested in finding the dominant contribution, what we would like is that we would like two conditions. One, the real f, I mean, it has a relative maximum, and imaginary f is constant. Okay, that's the thing. So in fact, so that we'll let me write down the conditions. Yep. So we'll in fact write down the conditions. So we want, so let's see. So there is some part of the path let's call it C naught. C naught is this part where imaginary part of, so there are three, let me write down the conditions. First condition, exactly, I'm just following this, that imaginary part of f is constant. So this is my C naught, this path, this bit of the path, C naught is constant on C naught. Second, that there is some point z naught where df by dz is 0, at z equal to z naught is 0. And finally, C. The C, so I mean the real F has a relative maximum. Okay. These are the three conditions. Now, it may happen that I mean the original path which is given to you, okay, may not have any such point. Okay. So this may be the original path, but it could be that but it's this F and G are analytic in some big region. Okay. Then it may be that you can of course deform this contour, right, because F and G are analytic, right. So you can deform the contour, and maybe after deforming you find a point Z0 and a little stretch of C0 such that this condition is satisfied. Okay. You can do that, and you can evaluate your integral there, because anyway this integral is the same as that integral to begin with, right. So this is all we are saying. So there is some somewhere. So practically what you would do, given such a object and it's you know the domain of analyticity, you try to find out first of all a point where df by dz is vanishing, right. Then you go to that point Z0 and then try to look at all possible directions, all possible C0 paths, right, because this condition has nothing to do with the choice of the path. This only depends on a particular point, right. These two informations depend on the choice of the path. So starting from the Z0, in different directions you move, this may or may not be true. The A and C conditions may or may not be true, right. So you have to choose that path where this A and C are satisfied. Okay. And then okay, suppose it happened that the path Z0 was this point and the path was like this. Well, you can still deform the contour like some such thing, right. So this is practically the way you will do. It may happen that your function is such that this is called critical points, the function, that there may be more than one critical points, maybe several points where df by dz is 0. Then you should include, so suppose there is Z0 and there is another point Z0 prime, then you should also try to include that, right. So choose a path which passes from all of this, okay. And then you'll get a little contribution from here, a little contribution from there, and then the final thing you can just add up all this. And the claim is that if W is very large, then this is a pretty good approximation to the integral. This is the statement. Okay, so let's try to analyze these conditions in a bit more detail. Okay, so let's make a Taylor expansion of the function f at Z0, around Z0. Okay, a general expansion, so f of z around Z0 will be f of at Z0 plus z minus Z0 df by dz at Z0, but that is 0 by assumption. So the first term vanishes. The first coefficient is 0. So then it will start with z minus z0 squared divided by 2 d2f by dz2 at z equal to Z0 and so on. This is where I am using the b, the fact that the linear term is absent. That's the. So you see again, so now you already see what is happening. We said that in general, if this is not Gaussian, it's not quadratic, you cannot do this integral. But going to near Z0 and making Taylor expansion, in fact, we'll only keep this term, right? So effectively, the problem becomes a Gaussian integral. See? This is what, yeah. Okay, so okay, so let's do the following. Let me just use the coordinates. So I am Z0. This is my point Z0, and Z is somewhere around here. So I write Z minus Z0 as R times e to the I. I don't know why in the book it is used the phi. Let me use the theta. So please, I mean, if you look at the notes here, it's a small phi. But since we always use polar coordinate theta, I will use theta. Okay, and furthermore, this is some complex number after all, right? This is some complex number. So again, let me use a polar decomposition for this complex number, meaning absolute value times the phase. So I will write 1/2 d2 f over dz2 is some capital R times e to the power of I capital phi. This is just the magnitude of that. This capital R is the magnitude of that, and that's just the I. Sorry. e to the I phi is the phase. That is a complex number. That just is some fixed number is given. I mean, fixed number meaning once you have a particular function, you just evaluate the two derivatives at the z naught, it will be some particular complex number, and I just take the absolute value and its phase. That's just notation. So let's so what is so f of z minus f of z naught, let's see. So take this here. This starts off with so this becomes r square capital R and e to the power of I 2 theta plus phi, right, plus higher orders, plus order r cube, right, because the next term will be z minus z0 cube, that will go like small r cube and so on. So the up to r square is this contribution. Okay. So now you see, now we want to look at the imaginary part and the real part, right? So let's take the real part and imaginary part of this. So what is, I can erase this. This is just a Taylor expansion. So let's take the real and imaginary part of it. So real part of fz minus fz naught is just r square capital R and then cosine of this, right? Cosine of 2 theta plus phi plus order r cube. So I mean I will keep only plus when I put dots I mean order r cube. This is up to small r square. And similarly imaginary part of fz minus fz naught is equal to r square capital R times sine of 2 theta plus phi plus dot. Okay, so let's see. I mean the real. So let's look at this in a little bit more detail. Let me draw some picture here. Actually, let's simplify this. No, okay, it doesn't matter. So when 2 theta. I mean, let's look at when this is positive and when this is negative, right? So 2 theta plus phi is between minus pi by 2 to plus pi by 2. Cosine is positive, right? So let me write down cosine. This is positive, right? And between pi by 2 and 2 theta plus phi and less than or equal to 3 pi by 2, this is negative, right? Okay, at the limit, at the end points is 0, of course. So I mean when I say plus meaning is greater than or equal to 0, when I say minus meaning less than or equal to 0. And then from 3 pi by 2 to 5 pi to 5 pi by 2, it's again positive, and then 5 pi by 2 to 7 pi by 2 is again negative. So let's try to draw. So this means I can erase this. You'll remember this. I mean, from this now, I've already taken into account this second condition, df by dz. I mean, that was already in the Taylor expansion, right? Now what I have to do is real part I have to make it relative maximum, and the imaginary part I want to make it constant. So this is what I want to do. So this just please remember that, because I'm going to erase this. Okay. So what does it mean? I mean, you might wonder why I have done that. After all, 3 pi by 2 is the same as minus pi by 2. So why I'm writing this thing? This looks like the same as that, right? But it is not, because I want to look at how the theta changes. You see, if 2 theta plus phi is between this, theta is between minus pi by 4 plus pi by 4, right? So I mean, let's rewrite that for theta. So let's write down this thing. Theta is between. So let's take the phi on the other side. So minus phi by 2 minus pi by 4, and here you get minus phi by 2 plus pi by 4. So this cosine is plus, okay, and then minus phi by 2. I mean, just shift it by that, plus pi by 4, and here you get minus phi by 2 plus 3 pi by 4, right? Theta, this is minus, then minus phi by 2 plus 3 minus pi by 4. This is plus again, and then minus phi by 2. 5 pi by 4. Okay. And now you see that this is not the same as that, right? Because this is from minus pi by 4 to plus pi by 4. This is 3 pi by 4 to 5 pi by 4. Minus. Okay. So this is what how the sine cosine is behaving. Cosine of that 2 theta plus phi. Okay. So in this region, you see, whenever you see it's plus, it means that real part of f minus fz minus fz naught is positive, right? That means along these things, real fz will not be a relative maximum, right? Because this is so, right? I mean, erase this here. So this situation is this. So z naught is some point here, right? And then z. So let's draw the. So here is my this parallel to the real axis. That's parallel to the imaginary axis. Z is some point here, and we are taking this angle theta, right? Because theta z minus z naught was small r times. Maybe I should draw bigger, otherwise you cannot see. So here is my z naught, okay, and here is z, and this was the angle theta, right? I erased that, but you remember z minus z naught was a small r, which is a length, times e to the I theta. Okay, so what we are seeing is that, and let's say phi is some angle. So I don't know. Phi. So let's say this is minus phi. Okay, because here minus phi by 2. Sorry. Okay, minus phi by 2 is some. I mean, phi by 2 is some number. So minus. I just draw my minus. Assume phi by 2 is positive, then minus phi by 2 will be that. So here it is saying this minus pi by 4. Shall I, for simplicity, assume that capital phi is 0? I mean, it's easier to draw. If capital phi is not 0, just shift the entire picture at the. Okay, so let me first draw the picture for phi equal to 0. So assume phi equal to 0. Capital phi, I mean, equal to 0. So in that case, I can just draw it more easily. So you see, this guy is 0. Huh? So from minus pi by 4 to plus pi by 4, which means when theta is, so theta between this to that, okay, minus, this is minus 45 degrees, that's plus 45 degrees. Here, in this entire region, it's plus, okay. Then pi by 4 to 3 pi by 4, which is this region. So let me forget these lines. So this is, here it is plus, here it is minus, here it is plus, and here it is minus, right? So if a point z is somewhere here in this region, then fz, the real part of fz here is greater than the real part of f here. So if the path was going in anywhere in this like this, then it will not satisfy the third condition, because as you go along the path away from z naught, real part is increasing, right? So you shouldn't choose a path here. In fact, you should choose a path in this part, right? Because as you go away along this direction or along that direction, anywhere along this direction or that direction, etc., real part of f is becoming less than the real part of f evaluated there is becoming less than the real part of f evaluated there. Okay. Okay. So that's the situation. What about the sign? But you see, also on the other hand, we also want to keep the imaginary part of f fixed, I mean along the path. That means sine of 2 theta plus phi, again let me assume phi is 0. Sine of 2 theta, capital phi is 0, then sine of 2 theta should be 0, right? If I want to keep the imaginary part constant along the path. I mean, all of this exercise I am doing is true. I am given this point z0. Now, I want to see what is a path, right? That's our aim now. What is a path? So, I want imaginary part to be fixed, to be constant, which means this must become 0. Okay. So, that means, so assuming capital phi is 0, sine of 2 theta is 0, which means theta is 0, pi by 2, pi, or 3 pi by 2, because 2 theta should be 0 or pi, right, or 2 pi. So, if you want also sine of 2 theta, assume capital phi is 0, is equal to 0, then that implies that theta is equal to 0, pi by 2, 3 pi, pi, and 3 pi by 2, right? These are the possible values. So, which means the sine is 0 along this direction. Maybe I should, how shall I put it? There is no other color here, right? Difficult to draw. Ah, there is a green color. Okay. So, here along this line, along this line, along this line, and along this line, sine is 0. So, sine is 0 in the green line. Sine is 0 on the green line. Okay. So, I could have chosen any of these paths, either this path or that path, and that will satisfy the first requirement, that the imaginary part is constant. But of these two possible choices, which means that either I can choose a path like that or like that, right? Of these two possible choices, in one choice, actually the real part is increasing, right? In fact, it's increasing by a maximum amount, because precisely for in that direction, cosine is the highest, is the biggest value, right? You see, phi is 0. So, if theta equal to 0 or pi, cosine of 2 pi is 1, plus 1. There is a maximum value. So, here it is increasing the most rapidly. On the other hand, if you take the path along this direction, again the imaginary part is fixed, is constant, but now the real part is decreasing, and actually is decreasing the fastest way, right? Because again, for theta equal to pi by 2 or 3 pi by 2, 2 theta is either pi or 3 pi, right? Cosine of pi or 3 pi is minus 1, is the most negative value that cosine can take, right? So, it's the most rapid decrease. Okay. So, this is the correct path. This is the path that we should choose. Okay. And this path will satisfy all the three requirements. Okay. Now, if capital phi is not 0, okay, you just rotate this whole picture by minus phi by 2. Just rotate the whole picture. Okay. That is all, because that's a shift, a fixed shift from in the ranges. Okay. So we choose, so our path will be this one. This is our path, C0. Okay. Passing from Z0 along this direction. And it's in that direction that this is the maximum. I mean, this f decreases most rapidly as you go. I mean, the real part of f starts decreasing most rapidly. So, if I try to draw, I mean, in a three-dimensional kind of picture, so say I don't know if here is my, and here is I draw the real part of f, okay, and say the point z0 is somewhere here. So, this is some point, this is the real part of fz0. This is the real part of fz0. Then what we are seeing is that, so we have this what shall I call, I don't know. So, let us say these lines are down here. So, these green lines are here. Okay. In one direction it is decreasing, other direction it is increasing. Okay. So, the picture is like, as I go along that, it's increasing. So, it goes like that. So, this is along this direction. Okay. But as I go along perpendicular, I mean, here this is actually perpendicular. Okay. As I go along that direction, is decreasing. So, can you imagine what it is? I mean, it's like it's a saddle, right? It's a horse saddle. Right? So that is why it is called saddle point approximation. Okay. So, I mean, so it's like in one direction it's going down there, in the other direction it goes like that. This is the way the horse saddle looks like, right? The saddle of the horse. Okay. So having done that, then now we can just immediately carry out the integral. So this is my path C naught. I choose this path, and so along that path we can just integrate this. What shall I do now? Erase this thing. Maybe this is not important. So I go back to this integral e to the w f. Now f is f z naught plus z minus z naught square times 1/2 d2f over dz2 evaluated at z naught plus dot 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 times g of z. Right. So let's change the variable. I mean, so this was r square, right? So remember, z minus z naught is r e to the I theta, and half d2f over dz2 was capital R e to the I phi. So this becomes e to the w f z naught plus r square times e to the 2 I theta plus e to the power of I 2 theta plus phi. So what was the value for this? This is 2 theta. Theta is pi by 2. So 2 theta plus phi. I mean, this is the value of 2 theta plus phi actually. This is the path we want to choose, right? 2 theta plus phi is 2 theta plus phi is what? I mean, so this is the theta. So 2 theta is actually pi. So 2 theta plus phi is pi or 3 pi, right? These are the values, right? In this region. I mean, this is, I mean, forget the phi. I mean, that picture is for phi equal to 0, right? So here, this is theta equal to pi by 2. So 2 theta is pi. And this is theta equal to 3 pi by 2. So 2 theta is 3 pi. Of course, in both the cases, this becomes minus. This becomes e to the I pi or e to the 3 I pi is minus. Okay? I mean, that's exactly why we said it is is the fastest way it is decreasing. Right? That's what it should. So this becomes a minus sign. So I can as well forget that along the path, along the small part of the path that I'm going to integrate. It's minus. That's just the faces minus. Times, okay, capital R. Capital R was just the modulus of that, 1/2. So let me just write as capital R. So this is what I have to integrate, and then times g of z, plus dot dot dot, and then g of z. Again, let me do the Taylor expansion. So again, g of z naught plus z minus z naught dg by dz, etc. So this is the integral I have to do. Remember, this is order r cube. Right? Now you can see that this is indeed dominant because in the large W limit, because I mean, so when I'm integrating this here, I'm basically integrating r, right, dr, from whatever some. I mean, from 0 to infinity, basically 0 to some value, 0 to some value. Okay. So I mean, so I can, you see, I can absorb this W inside here, right? By redefining R goes to R divided by root W. Okay. Then this W disappears here. I mean, this is a constant. I can take it out of the integral, right? So that goes away. This part is simply that W disappears. But here you see, if I take R cube, okay, R cube term, when I do this, you will get R cube divided by W to the power of 3/2. So one W cancels, but still what is left over is square root of W. So in the large W limit, all these are very small. You can ignore. So if you wish, you can actually bring this down from exponential. All these higher terms you can start bringing them, making an expansion. Okay. So that together with this are also going to give you powers of r. Right. So this will be a so let's write down. So this I can rewrite. So this whole thing I can rewrite as e to the power of w f z naught, that is outside, and then I have dr e to the power of minus w r square, capital R, times the first term is simply g of z naught, and then there will be an expansion 1 plus r plus with some coefficient plus r square times some coefficient and so on and so forth, right. This will be the general term. I can start expanding this part as well as that part. First term is gz naught, okay, which I take out, and then okay. Now if I go through this definition, r goes to r over root w, then this goes away, w goes away from here, but in all of these things I will get a root w, root w, w and so on in the denominator. Okay. So in the large w limit, those will be very small compared to the first term. Okay. So this is the idea, and you can do the first term is just a Gaussian integral. Okay. I mean this is just a Gaussian integral, and I'll just write down the result. This integral you already know, and the result is so the final result is IW is equal to, I mean this is the contribution from the Z naught part, I mean from the C naught part of the path, is approximately equal to e to the power of W f Z naught, which was outside the integral, and then what was the result here? C naught. You see that you can see immediately there will be a 1 over root w, right, because when I scale do the scaling, this w disappears, but from the measure I will get a 1 over root w, right. So there will be 1 over root w, and then there are these other pieces, this capital R will also appear times capital R also, yeah, because you can also scale by capital R also, so that also disappears. Okay. So you get that. I mean the explicit, there are some root pi factors, what is root pi or C naught, what is C naught? C naught is the first term times the gz naught, yeah, gz naught, and then there is a root pi. Root pi is simply the integral. So remember, although I am integrating over a very small r, right, I mean remember it was that path, that stretch of a path, this was z naught, and then from some region where it is valid, but it does not matter. You see, this is exponentially suppressed. W is very very large, so this is a peak like that at here, right. So even if you extend the integral from minus infinity to plus infinity, it does not matter, the error will be very small. Okay. I mean in reality the integral is from some part from some value to some value, right, along the path. But if you draw this exponential, this is like peaking here and very rapidly going to 0 here for large W. Okay. It's a Gaussian, this peaks, and the larger the W is, the faster it goes to 0. Okay. So for large W, you will not make much error if you extend the integral from minus infinity to plus infinity, because the contribution will be very very little for large W. Okay. So you might as well do this integral to minus infinity to plus infinity, but there you know the Gaussian integral gives you root pi. That's the origin of the root pi. Okay. So this is basically the term, the leading term, and then there will be order 1 over, so 1 over root w is outside, then there will be order 1 over root w or 1 over w type corrections. Okay. But for the leading w, this is the first term already gives you very large w, the first term already gives you a pretty good approximation. This is the idea. Perhaps I should just give you one example, and because that example will be useful. The use of this, as I said, in quantum mechanics is anyway used, but let me take an example, because this will be important for us actually, this particular example. So let's consider this integral IW equal to what is this? I need my specs. E to the minus z, integral e to the minus z, z to the w dz, 0 to infinity. So this is the integral. The next chapter, next section we will be studying will be gamma function, and you will see that this is a representation of gamma function. Okay. So for that, that reason I wanted to give this example. So we want to find the dominant contribution for in this integral in the large W limit. Okay, that's what we want to do. So the trick is, you see, this is not quite in the form that we remember. Our form was this e to the power of W f times g, right? But so W is appearing here. Okay, of course you can rewrite this. Z to the W is the same as e to the power of W log z, right? But it's more convenient to write it in the following way, because there is this z. You see, z is goes much faster than log for large z, right? So it is better to also put a w here. Okay, and that you can do by just change of variable. Just write z equal to w psi. Okay. After all, z is a dummy. It's an integration variable. I can write it like this. Okay. And then this integral becomes 0 to infinity. E to the minus z becomes e to the minus w psi, and this becomes there is a w to the w comes out, right? You substitute this, and w you're not integrating, so that comes out, and then psi to the power of w, which I can write as plus w log psi, right? And then dz just gives you d psi, and there is a factor of w, so this w to the w plus 1. Okay, so now we want to look at this integral. So first of all, so you see I can take out w as a common factor, and you just get here log psi. Okay, and let's see, let's try to find the critical point first of all. So this is my function f as a function of psi now rather than z. So you want to look at the point df by d psi is 0. Okay, so df by d psi is simply 1 plus 1 over psi. Sorry, there's not a minus. There's a minus inside here. If I take out a minus, there's a minus. Initially it was that, no? Minus w psi, and then from here you get plus w log psi. So I take out a w. So if I take out w, then it's minus psi plus log psi. So in fact it's minus 1 plus 1 over psi. Okay, this is my function f. So the critical point will be exactly psi equal to 1, right? So psi equal to 1. This is my z naught, psi naught equal to 1. Okay. And now you can expand this function around psi naught equal to 1. Okay, so you remember we want to make a Taylor expansion, right? So you start with at psi equal to 1 itself, log of 1 is 0, right? So this goes out, and this is minus 1. So f becomes minus 1. Start first point, first value. Then the next term of course will be 0 because df by d psi is 0. So then you get psi minus psi naught. Psi naught is 1 square times 1/2, and the second derivative of this evaluated at psi equal to 1. Second derivative will give you minus 1 over psi square, and then evaluate at 1, so it's just minus 1, right? So this is minus 1. Okay. And now you see that if along the real, I mean in fact, so now look at the path. What is the path where f has a relative maximum, right? You see, so let's draw this, let's remove this. So here is the xi plane. Now if you look at the real axis of the xi, and this is my point 1. Remember, this is the point psi naught equal to 1. This is the point psi naught. So if you go along the real direction, right, either side of the 1, okay, this is positive. Okay. So f, the real part of f will be decreasing, right? And not only that, imaginary part is in fact on the real axis, imaginary part is 0 actually for this. So imaginary part is constant. So all the conditions satisfied if you integrate over the real part, right? Is it not clear? No. No. So this is my function, right? This is the Taylor expansion. I mean, plus higher order terms, plus order psi minus 1 cube. Right? But let's ignore that. Let's just keep here up to this point. So let's look at. I mean, from here, I want my path to pass from here, but now I want to determine which path I should choose. Suppose I go along this direction, along the imaginary direction. So psi minus 1, I mean remember this is psi naught. Psi minus psi naught is pure imaginary. But if it's pure imaginary, this becomes negative. So including that negative sign, it becomes positive, right? So f will a real part of f will increase as you go along that direction, right? No, that is a fixed value. That's a constant. That's the value of f at this point. Now you want to ask, as you go in different directions, whether the real part increases or decreases, right? This minus 1 is the value of f at psi naught equal to minus 1. Right? So as you go in this direction, you see that a real part of f increases, right? If you go in this direction or this direction, real part of f decreases. You want the real part of f to decrease because you want a relative maximum, right? So we should be choosing this path, and in fact it's in this direction that it decreases most rapidly, right? So this is the steepest descent. That's why it's called steepest. So in this direction it decreases most rapidly, and furthermore, the imaginary part of f is constant along that direction. In fact, imaginary part, when the psi is real, imaginary part is 0, right? So imaginary part is of course constant. Okay. So this is the right path, right choice of the path, which satisfies all the 3 conditions. Okay. So now I can just substitute this and integrate. So the result is, so this integral, now I can erase this part here. So this integral is simply w to the w plus 1, and then when I expand, so there is e to the power of minus w, when I substitute this f here, right, times the integral 0 to infinity e to the power of minus w times divided by 2 psi minus 1 square. Not, yeah, 0 to infinity, psi minus 1. So, really just, I don't even have to deform the contour. It's already the real line which satisfies all those conditions. Plus higher order correction, which I'll ignore. I'll just look at the leading term. Now this integral, although it's from 0 to infinity, let's change the call psi minus 1 as some x. Okay, so this becomes x. So I can erase this. So let's focus on this, the integral itself. So this becomes, I mean, this d psi. This becomes e to the minus w by 2 x square. Psi minus 1 is x square. This is dx, and the integral becomes minus 1 to infinity. But once again, since for large w this is exponentially suppressed, I mean Gauss is suppressed very rapidly, I can, without making much error, I can replace it by minus infinity. Okay, and then this integral is simply root pi, right? Root w by 2, root 2 by w times root pi, root 2 pi by w. This is a Gaussian integral you can perform. So we are seeing that the leading behavior for IW is there is a 1 over root w, so that makes it w to the w plus half, w to the power of w plus half times e to the minus w times some number root 2 pi. The important point is here, you see, there's a huge growth. I mean, if you, okay, you might wonder that what happens with minus w, e to the minus w, but you can rewrite this in the exponential, e to the power of w plus half times log w minus w. So this is w log w goes faster, I mean, is larger than w for large w. So this grows very rapidly. I mean, this is a times root 2 pi. Actually, you will see later on, I mean, the next lecture, I will just stop now, next lecture, this is in fact a representation for gamma functions. And gamma functions, I mean, there's a gamma of, say, w, there's a function which is defined. But in particular, if you take w to be integer, that's nothing else but the factorial of w. If w is integer, so take gamma of n, this is simply factorial n minus 1. Okay. So this kind of an estimate tells you, and remember w is n, right? I'm taking w to be integer. Right? There's like gamma of n minus 1, factorial n minus 1, and you are looking at this object in the large n limit, large w limit, which is large n limit. So you are seeing how this factorial behaves for large n. Okay. That's very important in statistical mechanics, because the factorials are basically related to the various probabilities and so on. No? So when you sometimes are interested in the case when there are large numbers, how the probability behaves in terms as a function of large numbers. So this formula is a very, very important formula actually. This formula is called the Stirling formula. Stirling formula. It has extensive use in statistical mechanics. I mean, you will not realize it. The next time I will show how gamma function is related to this and so on.